Today we are going to cover section 3.10, differentials. So some definitions. Let y equals f of x be a differential function, then the differential of x, d of x, is an independent variable and may take on any value. The differential of y is defined as dy equals the derivative of x dx, and depends on the values of x and dx. We know a curve is very close to its tangent line, near the point of tangency. In fact, as one zooms on the point, and the graph looks more and more like its tangent line. This is the basis for a method of finding approximate values of functions. It is not easy to calculate values on a curve, f of a, so we will settle with the values of the tangent line of f at a f of a. Therefore, we use the tangent line at a f of a as an approximation to the curve y equals f of x when x is near a. An equation of a tangent line is y equals f of a plus the derivative of f of a times x minus a, which we have covered already. But the approximation, f of x, is approximately f of a plus the derivative of f of a times x minus a. This is called the linear approximation or tangent line approximation of f at a. The linear function whose graph is this tangent line, that is, f of x is approximately f of a plus the derivative of f of a times x minus a, is called the linearization of f at a. So, example 1. Find the linearization of the function f of x equals square root of x plus 3 at a equals 1. Then approximate the square root of 3.98 and 4.05. First you need to find the derivative, then plug in 1 into both the original and the derivative, then into the linear approximation formula, then solve. So first, like I said, find the derivative, which is right here. The derivative is 1/2 x plus 3 to the negative 1/2. Then plug 1 into both the original and the derivative. If we plug it into the original, we get 2. Into the derivative, we get 1/4. Then into the linear approximation formula, which means we have 2 plus 1/4 x minus a, which equals 7/4 plus x divided by 4. Which is, now we can say that an approximation for the square root of x plus 3 is 7 divided by 4 plus x divided by 4. So here's a graph that shows what we just did. It's really hard to find it on a curve, so we found points on f of x, and we know that they are approximately that value. Now we can approximate square root of 3.98 and 4.05. This can also be done with a calculator, but the linear approximation gives an approximation over an entire interval. Below you can see the estimates from the linear approximation in example 1 that I just went over. Here are the true values. Notice that the tangent line approximation gives good estimates when x is close to 1, but the accuracy of the approximation deteriorates when x is further away. So for what values of x is the linear approximation accurate to within 0.05? So we want to know when what we just found is accurate. So we're going to find the difference of them when they are less than 0.5. Now, when it's an absolute value, then we don't know if 0.5 is negative or positive. So we have to write it as such and solve with that information. So that means the linear approximation should lie between the curves obtained from shifting the curve y equals the square root of x plus 3 upward and downward by the amount of 0.05, as you can see right here with what I've done. This was the original curve, the one in the middle, shifted up 0.05 and down 0.05. Thus we can see from the graph of the approximation where these points are. And we can estimate the x-coordinate of P is about negative 2.66, and the x-coordinate of Q is about 8.66. So now we know that this is accurate within negative 2.6 and 8.6. Similarly, in figure 4, you can see that the approximate is accurate within 0.01. And it's the same kind of situation. We do value minus 0.01 and plus 0.01, find the x values and put it between those values, and we can see where it is accurate. Geometrically, if we think of the change of x as the change in x, then change in y equals f times x plus change in x minus f of x is the change in y, corresponding to the change in x. Therefore, if the change in x is really, really small, we can assume that the change in y is equal to dy. So, compare the values of change in y and dy if y equals f of x equals x cubed plus x squared minus 2x plus 1. And x changes from 2 to 2.05 and 2 to 2.01. So what we simply do is change 2 to 2.05. And we get our value. And then we plug it into that formula that we just discussed, so f of 2.02 minus f of 2. So we take 9 minus the 9.717625, and therefore we get dy equals the change in x times d of x, which could be written also as 3x squared plus 2x minus 2 times dx. Same thing follows for the next one. When x is 2, it becomes, we can plug in 2 into the formula, 0.7. We plug in 2.01, 9.14. And we can follow in the same formula as we just did, subtracting 9 that we found from the original up here at the top, subtract 9.140701, and we would get this for the change in y, from 2 to 2.01. And then, of course, we can plug in to the formula, the 2.01, and then we would get our difference to be 0.14. So what if I give you another problem? The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? If the radius of the sphere is r, then its volume can be represented as 4/3 pi r cubed. If the error in this measured value of r is denoted by dr change in r, then the corresponding error in the calculated value of v is the change in v. So we can find the derivative, correct, which would be 4 pi r squared. And then when r is 21 and dr is 0.05, we can plug these values in. 4 pi 21 squared times our dr, which is our change in r, 0.05. So the maximum error is in the calculated volume is about 277 centimeters cubed. And that's it. Make sure you complete your web assignment.